Good day, everyone. You are welcome back to Real Class. And I remain Engineer Shegun. Today, we'll be talking about current electricity. Now, electric current is simply the flow of charges. And basically, we can define current I as the number of electric charge passing through a point divided by the time it takes. So current is charge over time, and current is measured in amperes. There are some devices that offers a very high resistance to the flow of current, and these devices are called resistors. Those devices that does not offer or offers a very low resistance to the flow of current are called conductors. Of course, I can say that also devices that offer a very large resistance to the flow of current are also insulators. So resistors are special form of insulators which are used in electric circuit to actually reduce or resist the flow of current that's flowing through that circuit. The next thing I would like us to talk about is electric energy. So simply put, electric energy E or electric work is simply ITV, where I is time, where I is current, T is time, and V is voltage. There is a very important law that tells us the relationship between current and voltage, and that law is Ohm's law. Ohm's law basically states that the current flowing through a metallic conductor is directly proportional to the potential difference across its end. So if I'm to write Ohm's law, I will say V is directly proportional to resistance R. It's directly proportional to current I rather. V is directly proportional to current I, because the current flowing through a conductor, is directly proportional to the potential difference across its end. If I introduce a constant, I will have V is equals to RI. But just to write it very well so that it will look like the things that we have been saying before, V is equals to IR. R is my constant of proportion. Having said this, I can come back to electric energy. Here I'm using E to represent electric energy. And in some textbooks, they'll show you more than one equation for electric energy. But I don't really need those other ones. I can show you like 3 of them. Because I may ask you to find electric energy, and you are giving current, you are giving time, you are not giving voltage, and you need to find electric energy. And you know that you need voltage to be able to find electric energy. But they give you resistance instead. From here, from Ohm's law, I can find my voltage, and after finding my voltage, I can put it into this place, and I can find my electric energy. So person will just say, why don't just put in the value of V into this place from here? And if I do that, I'm going to have E is equals to ITV. IT, then instead of V, I'll write IR. Now, E will now be equals to I times I is I squared CR. And this is what I'm going to have. This is another formula they will say for electric energy. But I will not encourage the student to memorize this. Know this and know Ohm's law. You can always get this at any time. Or you could say, maybe in a question, I need you to find energy, electric energy. And I'm giving it, and I've given you time, I've given you voltage, I did not give you current. I can still come back to Ohm's law again. And I can say that from Ohm's law, since V is equals to IR, then means that I will be equals to V over R. But we just said now that electric energy is ITV. So that means anywhere I see what I'll put V over R. And if I do that, I will have E to be equals to V. I will have E to be equals to V over R TV. From here, I'll have V times V is V squared T over R. And then they will say we have 3 equations for electric energy: number 1, number 2, and number 3. But you don't need to know this extra 2. All you need to know the first one and know Ohm's law. You can always get these 2. What are those factors that affect the resistance of a metallic conductor? The factors that affect the resistance of a metallic conductor, or the factors that affect the resistance of a resistance wire, includes the following. Number 1, we have length. How does length affect resistance? I can say that the resistance of a resistant wire or a metallic conductor is directly proportional to the length, which means the longer the wire, the more the resistance. That is one. Number two is area, or I would say cross-sectional area. Cross-sectional area. How does the cross-sectional area affect resistance? Resistance R is inversely proportional to the cross-sectional area. What do I mean by cross-sectional area? If this is my conductor, this is what I mean by cross-sectional area. This is the cross-sectional area, this point. The bigger the wire or the thicker the wire, the more the cross-sectional area. And of course, since we just said that resistance is inversely proportional to what? To the area, which means that the larger the area, the smaller the resistance, and the smaller the area, the larger the resistance. Another thing that affects resistance is temperature. For a conductor or for a metallic wire, the higher the temperature, the more the resistance, and the lower the temperature, the less the resistance. So from factor 1 and factor 2, I can write another equation which will look like this. Remember, we just said that resistance is directly proportional to length and inversely proportional to area. I'll introduce a constant. Now say resistance is equal to resistivity length over area. R is resistance. This is my constant here, resistivity, this is the length, and this is the area. From here, I can say the following. If I make resistivity subject to formula, I can have resistivity to be equal to resistance area divided by length. And for a particular wire, I can say for a particular wire that R1, A1 over L1 is equal to R2, A2 over L2. I can also say that R1 squared over L1 is equal to R2 squared over L2. Here, this capital, this capital letter R here is standing for resistance, but this small letter R is standing for the radius of the wire. A is standing for the area of the wire. Small letter R here is standing for the radius of the wire. I can also say that R1 D1 squared over L1 is equal to R2 D2 squared over L2. Here, D is the diameter of the wire. So having said all of this, the next thing that is important for us to know is the electric power. And electric power is not really a difficult concept because we already know that power generally is the rate at which energy is being expended or the rate of doing work. So power is equal to work over time. Then I can say that power is equal to, when we say work or energy over time. So of course, I can even replace this W with E if I want to. Then remember I told you that E is ITV, right? So I can say ITV over T. Now this T cancels out this T. So I can say electric power is just IV. From this up part, if I make this E subject to formula, I can say electric energy is PT. Which of course, it can be either electric energy or electric work done. If power is equal to IV, I can have other expression of power, all coming from Ohm's law. And remember, Ohm's law is V is equal to IR. So if I substitute the value of V equal to IR here, I will have a different equation. And if I make I subject to formula and substitute it into here, I will have a third equation. Those two extra equations, you don't need to memorize them. Just know what power is, know this, and also know this expression. The next thing we need to consider is the arrangement of resistors. And we are going to explain that in our next class. Good day, everyone, and welcome back to Ray class. Today, we'll be talking about the arrangement of resistors. Remember, resistors are electrical components that are used to offer a resistance to the flow of current. Now, the symbol for resistors can be like this, drain, zigzag lines like this, or I can use a box like this to represent resistor in an electric circuit. Now, if you see a straight line drawn through the box, then that is a variable resistor or a rheostat. How do we arrange resistors in series? Just as I've drawn here. And it's very easy to know resistor in series if there's no branching between them or there's no junction. If the current that's entering this resistor R1 with the same current that will come out of it and enter R2 and come out of it and enter R3. So everything is already in series. This one is the reverse of what we learned in capacitors. If you are asked to find the total resistance of these resistors, or the equivalent resistance of this resistor, or the resultant, it all depends on what word you want to use. Then I can say that RO total will be equal to R1 plus R2 plus R3. So if resistors are in series, all I'm doing is just adding them up. It's that easy. If there were to be 4 here, I'll add the 4th one. The unit of measuring resistance is in ohms. And the symbol for ohms is this. So I can either say 2 ohms like this, I can write 2 ohms. Now, if resistors are arranged in series, the potential difference across them, of course, will not be the same. But the current flowing through all of them will be the same. All right? So take note of that. Let's come over to parallel arrangements. For parallel arrangements, if I'm to get an equivalent resistor or the total resistance, rather, if I'm to get equivalent resistance of the total resistance or the resistance of the combination, then this is what I'm going to do. I'm going to do 1 over RO total is equal to 1 over RO1 plus 1 over RO2 plus 1 over RO3. This is what I'll do to get the total resistance or the equivalent resistance of the combination. However, if there were 2 of them arranged in series, there will be no need to do this. Use this equation. If there are just only 2 arranged in series, then RO total will simply be equal to product over sum, which will be RO1 RO2 over RO1 plus RO2. Now this is when they are arranged in parallel. These parallel arrangements and these series arrangements. So what we are going to do now is to take questions on all of these things that we have studied and see how we can easily answer them in our next class. Welcome back, and this is our first question on current electricity. Now, according to the question, a conductor has a diameter of 1.0 millimeter and length 2.0 meters. If the resistance of the material is 0.1 ohms, its resistivity is, and these are the options. So we set out our parameters. They have given us length to be 2.0 meters. They give us diameter to be 1.00 millimeter. I need to convert to radius. I need to divide by 2 to get radius, which is 0.5 millimeter. Resistance is 0.1 ohms. Now, from resistance, I know resistance is equal to resistivity length divided by the area. I'm looking for resistivity. So I'll make this resistivity subject to formula by cross multiplying and dividing both sides. I will get resistivity is equal to resistance area divided by length. But area is pi r squared because they did not give us the area directly, they gave us diameter. From diameter we find radius, then from there we can find area because area is pi r squared, and that's what we did here. Now, from here we plug in our value. Resistance is 0.1 ohms, pi is 3.14 times, or we can say 3.142, but approximately the same as this, times 0.5 times 10 power minus 2 all squared. Everything here is our radius. Now, I'm doing times 10 power minus 3 because I'm converting it to meters. It was a millimeter. To convert to meter, I will either divide by 1,000 or multiply by 10 power minus 3. Now, it will be easier for me to convert this up part to standard form so that I can easily do my calculation. Move this thing backward once, I will get times 10 power minus 1 times 3.14 times 1 over 4. I change this by 0.5 to 1 over 4 because I will do 0.5 squared. 0.5 squared is same thing as 1 over 4. I'm doing this so that my calculation will be easier. Times 10 raised to the power minus 6. I'll bring this 4 down to make this 2, and that will be 8. So I'll have 3.142 times 10 raised to the power minus 7. And if I say 3.142 times 10 raised to the power minus 7 divided by 8, I should get 3.93 times 10 raised to the power minus 8 ohm meter. And that would be option A. So that is it for the question.